Chaotic that I thought I would make sure we're all on the same page. So here's what I got us for. Part 3.3a, and I think while I'm thinking about it, everybody get part 3.3a out. It should look like this. So we're going to pick up where we left off. And part 3.3b is really short. So 3.3a, everybody get it out if you have it. Yes,
This isn't mine.
that's not yours.
This one isn't anyway. No,
The other guy handwriting. Is this your handwriting? Sorry. Read, Aaron, I don't know. Okay, so here in a minute, and I'll go ahead and tell you what slide it's going to be. We're going to start where it says Orion. So 3.3a, I'm liking page. I got the bottom of page 2-ish. So kind of here is where we're going to start here in a minute. So just a hint, and I kind of said this. Remember, I asked you guys on Wednesday, I'm like, why doesn't everybody use these? So if a teacher gives you these being PowerPoint slides, you don't have it? I have it. If a teacher gives you those, I would drag them out and just at least doodle on them. Because for me, in my classes, sometimes I'll be like, hey, that's going to be on the test. And just that simple word, you could put a star next to that, or test, or something like that. So that's my hint. If a teacher ever gives you PowerPoint slides. For some of my other classes, actually students, they're bound, and students buy them in the bookstore. So that's where we're going to start. So you can see today we're going to actually do kind of an assortment of things. We are going to skip part 3.3c, which is extrasolar planets. But it's everything's so interesting in this class. Extrasolar planets, and I don't know if we'll come back to it, those are just planets orbiting other stars. And like we've talked about, most stars have planets around them. But I think we'll get to 3.4a, which I'll pass that out. Okay, any questions about today? And then Wednesday, actually, we need to kind of wrap things up, sort of-ish, because we're bumping up against a Unit 3 exam next Monday, so a week from today. A little guilty having it the Monday of Thanksgiving week, but that's just kind of how it goes.
That's how all the teachers are doing it. I have two exams that day and a book review.
So, because honestly, like if you go to most 4-year colleges, they take off the whole week of Thanksgiving. So it's just we kind of running out of time here. But Wednesday we're going to kind of finish up the majority of the material we're going to be covering for Unit 3. One of the things I want to hit hard is this idea of how stars live their lives. We need to talk about how stars age and how massive stars die. That means part 3.5, which is actually, it's up there in Canvas, but it's about just specifically about black holes. We may kind of sneak that into Unit 4. We'll see. So part 5, we're going to kind of consistent with what I've been doing this semester. This is my first semester to be doing some of these activities. They're kind of fun. I enjoyed the last one we did. We'll do an activity and or a video. Now, if we do a video, it's going to be a good one. So make sure bring your favorite writing utensil, take notes, and you get to use those notes on your exam. Okay, so I think that's kind of fun for me. So Monday will be your test. So what can you bring with you? You can bring any notes you took during the videos. So if we do one on this Friday, that will be 3 video notes. The things for the star kits. So honestly, the biggest thing for that thing we did Friday, I think, and I'm going to refer to it today if I can find my copy, is that 1-sheet color paper that shows the lives of stars. This is cool. Okay, this you get to have on your test. So how cool is that? Okay, you just need to know how to understand it. Then you can also bring your 4x6 note card. Okay, so any questions about all of that? Somewhere in there I need to kind of pencil in what your unit exam is going to look like. I'll make a unit review sheet, and then from that unit review sheet I'll make a review video. I'm hoping to have that done kind of by Wednesday-ish. We'll see. Okay? All right. Let's pick up where we left off. Yep, that's Orion, and I think we already did this. I mean, this is a beautiful Orion. This is a scary Orion. But they're both the same Orion. The thing here is we're like just kind of changing what wavelength we're looking at. So this is kind of the new star formation. So we said that new stars are formed in nebula. This is the nebula, one of the nebula that I photographed. I showed you on Wednesday. It's the Orion Nebula. So this is what it looks like in visible light, and this is what it looks like in infrared. So one of the things about the Orion Nebula that if you're looking at it through a telescope, people say, ooh, there's a trapezium. And the trapezium is just kind of this kind of bunch of these little stars, that are nice little hot new stars being born. Orion. Okay, Orion. All right. I didn't bring it in here, but the other day I brought in my little poster of Messier objects, and each box is a little different thing that's neat to look at in the nighttime sky. So, hey Courtney. So there are two types of clusters of stars, and as we talked about clusters of stars, it kind of makes sense because if you have a cloud, a giant cloud, you're like, I can have all sorts of stars being born there at the same time. Okay. So the two types of stars, there are open clusters, and it's got several names. This is actually the Seven Sisters, the Pleiades, M45, Messier Object 45. It's very much an open cluster. Now, I don't want to give you guys bad info, but sometimes through binoculars, people will call this the Little Dipper, and it does look like the Little Dipper. It does through binoculars, where this is kind of a handle, this is kind of a bowl. But I will tell you, and I don't know if, I will tell you, if you find the Seven Sisters or the Pleiades, they go by both those names in the nighttime sky, it's like this big, okay, versus the Little Dipper is like this big. Okay, so this is this big. Okay. The other type of cluster, and we saw one of these the other day when we were set up, is a globular cluster. I love globular clusters. Okay, so globular clusters, there's more stars, and they're tight, and they're like just in a sphere. It's just beautiful. They look 3D. And then open clusters, when we looked at that cluster under the W, or Cassiopeia, the other day, that was an open cluster. They just make different shapes. Okay, so globular clusters, as it turns out, like the slide says, globular clusters are relatively old stars, and these are relatively new stars. One of the unique things about the Pleiades, or the Seven Sisters, what are you doing, Miss Lily? Are you still looking for your thingy?
No, I got it.
Okay, you're just flipping through papers. I'm like, I don't know, multitasking, I suppose. But so one of the things is because you can kind of see this cloudy material here. That's just like extra nebulosity around an open cluster, which is kind of unique. Okay, more new clouds. Okay, one of the reasons I feel like I can just kind of flip through these is I have way too many slides on kind of this topic. This topic is kind of showing the formation of a star. This is actually a photograph, and this is a figure. So the difference is this is an artist's rendition of this actually happening. So what's happening early on, remember proto means kind of the beginning. Proto means not quite there. Protosun is the sun that's not quite there. Protostar is a star that's not quite turned on yet. So as they have this kind of, they have a disk part, that's my protostar, and they have jets of energy coming out, okay? So here we go, disk part, jets of energy, disk part, jets of energy, okay? So disk part, jets of energy, you know, this looks like, to me, it was taken in maybe kind of like we saw that scary look in Orion, the infrared region, not the visible. Disk part, jets of energy. Can't really see the disk part, but we can see the jets of energy. So that's a star in the birthing process, a protostar, not quite turned on yet. Okay, protostars, we gotta love them. All right. So one of the things on your test, and actually in that packet that you guys did the skit on Friday, the packet where you guys at the end we kind of talked about an HR diagram. You're going to want to be able to understand and create an HR diagram. So the HR diagram, of course, it has temperature, and temperature usually it does the hot to the cool, and we usually go the 7 spectral types. That's the O, B, A, F, K, M, okay? And then we go how bright it is, like what we call luminosity, brightness, and brightness increases. And then we end up with this kind of, this region of stars, okay, is what we call the main sequence. And a main sequence star means that the star has settled in. The main sequence stage is the step right after protostar. So protostar, not a star. Main sequence is a star. The big difference is that it actually is glowing, creating energy in its core. So here we see, these are like little protostars over here, and they are on their way to become main sequence stars. How exciting. So which one, this is in scientific notation with regard to years. So these are all protostars. These guys, protostars. Which one gets there fastest? Okay, so here are your options. This is showing you where 100 solar masses goes and becomes a main sequence star. This one is showing 0.1 solar masses goes and becomes a main sequence star. So the numbers I circled, 10 to the 4th and 10 to the 8th. Which one's bigger?
10 to the 8th.
10 to the 8th, yeah. So it's saying that if you are a small little nubbin, you are going to take 10 to the 8th years to go from a protostar to main sequence. If you're larger, you're only going to take, what's 10 to the 4th? What number is that?
1,000.
I'm like in
10,000.
10,000. 10,000. You're only going to take 10,000 years to get there. What did we say with regard to once you're on the main sequence? Which one lives its life faster? This heavy guy up here or this light guy down here? The heavy guy lives it faster. Faster, yep. And then the light guy just, man, long time. So it's kind of consistent with that. This is I think, an interesting little graph. So we can have a bunch of stars be born in the same cloud, molecular cloud. So here we go. If you have a molecular cloud, this is kind of the distribution of how many stars of different types you get. The pretty blue one, is that a heavy one or a light one?
The heavy one.
It is a heavy star. These red ones, light or heavy?
Light.
Light. From this graph, in the same molecular cloud, which one do you get more of? If each dot represents kind of how many you get of that kind. You got more red ones or more blue ones? You got more red ones. So honestly, these guys, you get a lot more of those. And here's kind of a fun little tidbit. When we look at the nighttime the stars, or we're admiring the stars in our nighttime sky, we're not going to see those red ones, but we are surrounded by red ones. Why would we see the red ones?
They're not strong enough.
They're not strong enough. They're dim. Yep, exactly. And kind of the renegade blue hot ones pop out because they're high luminosity. Yep. So a while back, I kind of talked about, we said these guys are massive, right? These guys on the HR diagram, massive. Massive. I should say high mass. How's that? High mass. And these guys are low mass. And we kind of started out, actually, there is a threshold. There is a limit. So the high masses are about, this is 150. I could sometimes say 100 solar masses. Remember, we go solar masses would be M subscript SUN, the mass of our sun 100 times, or 150. Somewhere in there is the upper limit to the mass of a star. Anything bigger than this, and basically, I think it can't settle down. It's just too big. It kind of sloughs off some of that material. And it's like, trims itself. And it's like, okay, I can be a high mass star, but I can't be bigger than 150 solar masses. The lower end, we said, was 0.08 times the mass of our sun. And I'm going to try to explain why that is. So here is, this has been our sun this semester. And we said in order for our sun to begin nuclear fusion, basically gravity had to kick in, which increased the temperature and pressure in the core for fusion to occur. If you don't have at least, what is 0.08? 8% of the mass of our sun, then you don't have enough, you don't create the conditions that a star needs to begin fusion. That sort of object, and I don't think our skit on Friday talked about this sort of object, is called a brown dwarf, a failed star. Actually kind of have a few slides talking about brown dwarfs. It's a wannabe. Some would say Jupiter, the planet Jupiter that orbits the sun, is a brown dwarf, a failed star. Okay. And this kind of, we'll be talking more about this a little bit when we talk about deaths of stars. We can think of it this way. For in that cloud where a bunch of little stars want to come to life, we basically have gravity kind of pulling in on that region to be that star, gravity pulling in on this region to be this star. This is my stellar nursery. Gravity pulling over here to become this star. Well, what happens is kind of is being shown here with the chairs. Okay, this would be all this room here before gravity kicks in. Okay, gravity kicks in and there's less space. There's less chairs. Okay, so it's kind of showing you kind of the shrinking down. All right, I think I just have some slides here. This one actually is too big to fail. No, this guy is, let's see, one of the most massive stars. You're looking at, from what I remember reading, it was 100 times the mass of our sun. It's kind of still trying to tame down into an object that can be a star. So my 3.3b is about brown dwarfs, the failed stars. There are a lot of brown dwarfs out there. If you think there are a lot of little red stars, there are a lot of, which are stars. They're just down here. They're not very bright. There are a lot of failed stars too. This is trying to highlight some of the brown dwarfs in Orion. Okay, brown dwarf simulation, where kind of you see the sun and you see, generally speaking, the brown dwarfs in our area. So, brown dwarf, a failed star, wannabe star. This one kind of from left to right gives you a little bit of temperature and size, kind of thinking of how that works. So, of course, the sun is a successful star. Remember that the sun on this HR diagram is about here. Okay, it's on main sequence and it's about halfway between the massive and the low mass. We've been talking about how hot the surface temperature of our sun is. You can see it's about 5,800 Kelvin. Gliese actually is it's a brown dwarf. So these guys are brown dwarfs. Okay, check out their relative size. Notice that the surface temperature of the star Gliese 229a, pretty hot. Still does not have nuclear fusion going on its core. Then we get smaller. Okay, oh goodness, I can't spell smaller. And what happens to the temperatures? They get smaller. What's happening? We're going 2,600, 950. What's the trend? What's the trend in the temperature of those? I've kind of highlighted 4. These guys are brown dwarfs. What's happening with their temperature? It's decreasing. Yeah, it's getting less. And which planet is this? That's Jupiter. Not really classified a brown dwarf. And its surface temperature is 125 Kelvin. All right, so that was actually a little bit about, that was finished up 3.3a, and 3.3b was the little bit about the brown dwarfs. I'm going to hand you out the next set of slides I want to do. So we're going to skip extrasolar planets for now. We'll see if we come back to them. Okay. So the slides I'm going to give you now, you need to take that first slide and put it next to it, because it does not apply. It was for a previous lesson. I gave you 3. Yes, ma'am. Oh, sorry, Miranda. All right, so the first slide, yep, put it next to it, because that would just confuse you. Okay, let's see what else we got. aging stars. Okay. Another star, the Ant Nebula. Nebula just means space that has some gas, some dust in it, instead of just nothing. And then, so they put words with it that kind of describe the picture. I don't know if it looks like an ant nebula to you, but it is called the Ant Nebula. Almost looks like it's got kind of this butterfly sort of thing. In Friday's little skit, one of the things that we talked about was the fact that stars get larger, some of them depending upon what their mass is, and they get bloated, and at some point they create this thing called a planetary nebula. And this actually is the planetary nebula. This is a figure of kind of what's going on inside an aging star. So the first one, A, actually is what our sun's doing. You guys would tell me that inside our sun, we have hydrogen plus hydrogen, creating helium and energy. That's what our sun is doing. That's what actually all stars that are on the main sequence, that's what they're doing. So we talked about how our sun is going to swell, and our sun is going to swell. And this is kind of showing you a later stage where it has helium in the very, very center, and we have some hydrogen fusion outside. We talked about brown dwarfs a little bit ago, just today, failed stars. We talked about white dwarfs. This starts with letter R. What are white dwarfs down here? What do we call those? What's another name for a white dwarf? What am I going to do someday? Thank you. Retired star. Yep. Our sun is going to become a white dwarf. So that's two dwarfs. We have brown dwarf, white dwarf, no connection. And then we have these guys down here that are red dwarfs. Okay? Why do you think they're called red dwarfs? Why do you think they're called red dwarfs?
Because they're small and low intensities?
They're small and low intensities, and their color is red. Their color is red. Exactly. When you write down this OBAF-GKM, oh, I missed the G, GKM, this is the hot blue stars, and these are the cool red stars. So the red dwarfs, actually red dwarfs have to be larger than 0.08, but they get to be up to about 0.4. So these guys right here do something different. When we talk about aging stars, they do something different. And here's what they do. They create helium. So think of the, yeah, I think that's right. Think of the helium as kind of the blue fuzz, okay? The blue fuzz, they create helium, but the helium kind of works its way out. Can you kind of see it working its way out? And fresh hydrogen works its way in. These red dwarfs, do they last very long, or are they short-lived? How many people think that they last very long? How many people think that they're short-lived? Wow, you guys are all going to fail the test.
Okay.
Yeah, works for me. I just teach it, and I do a pretty darn good job of it. I can listen to my notes, and I can say, I said that. I don't know if they were listening. I gave them notes. I don't know if they were taking notes. I did these creative things. I'm very enthusiastic about this material. So, yep. So anyway, so red dwarfs will live a long time because they're low mass, and they just kind of take fresh hydrogen from the outside, bring it in, and they can kind of keep that fusion going on in their core. But they won't ever bloat out. They won't ever become, what's this area up here? What do we call these guys?
The supergiants.
Supergiants, very good. Supergiants. Also kind of the red giants or the giants. Yep, I kind of give them 3 names. I don't know if all people who teach this would give them 3 names, but I do. Now these guys will never become supergiants or red giants. All right, so stars age and they kind of do different things. So I'm going to try to kind of break that down for you. The one sheet I gave you on Friday that, one sheet I gave you on Friday, the colored one, actually kind of talks you through the different life cycles. I was talking to my mom on the way to school here, and she's like, what are you going to teach today? And I say, how stars live their lives. And she's like, that sounds so interesting. So there's basically kind of 4 different scenarios how stars live their lives. All right, what else do we have? Betelgeuse. Betelgeuse, Betelgeuse, Betelgeuse. So Betelgeuse actually is this star in the constellation Orion. Betelgeuse actually is a swollen red giant. Okay. Actually, if it were here in our solar system, it would actually have the volume out to Jupiter. That's not good. So this was a slide I showed in the previous part where we're talking about these are protostars, remember? And you guys told me that actually 10 to the 8th is a big number and 10 to the 4th is a smaller number. Actually 10 to the 4th, 10,000 is pretty big, but 10 to the 8th is even bigger. So my point is these protostars actually arrive at what we call the main sequence. They kind of wiggle or move on this diagram. This diagram is called the HR diagram. Okay. Well, here we go. What's the difference between this one? Okay, I'm going to have you kind of focus on this little arrow. These little arrows are all showing you the protostar going to form the main sequence stars. What about this arrow, these arrows? What's different about them? They're going the opposite way. They're going out here. What did you tell me was over here?
The giants.
The giants. So when we say that a star moves on the HR diagram, that's what we're talking about. It kind of changes its surface temperature and its luminosity, so it wiggles back off. Now what won't wiggle back off are these actually light guys down here. They'll just kind of keep on here, and I think they might kind of migrate over here. You guys told me these were white dwarfs. Okay, so they kind of become bigger. But I don't want to minimize this main sequence. Main sequence is where the star spends the most of its life. The most of its life. Clusters, star clusters, so this would be a globular cluster. Okay. And trying to highlight the main sequence stars. So these are main sequence stars. Most stars that we see in the nighttime sky are main sequence stars. Most stars are red dim stars. We can't see them. Okay. It's an open cluster. I've not ever seen this open cluster before. Beautiful. Notice we have some color differences here. With regard to temperature, I'll call this guy A, and just pick a random beautiful star. This guy B. How many people think that A is the hottest star? How many people, up between the two, how many people think that B is the hotter star? Me too. Well, you guys might guess. That's what I'm hoping for. So another HR diagram, a lot of HR diagrams. We have this diagonal, right? Main sequence. We kind of have these other regions, white dwarfs, giants, red giants, supergiants. These dots represent different stars, okay? This actually is a young cluster of stars. And, all right, so if this, I'll ask this in the form of a question. I'll put protostar here. Is this protostar going to go this way? I'll call that A, or is a protostar going to go that way? I'll call it B. How many people think it's going to go in the direction of A? How many people think it's going to go in the direction of B? It's going to go in the direction of B. Protostar, it still means it needs to arrive at the main sequence. Okay, we're going to call these massive or high mass up here, because they always are on an HR diagram. High M, I'll call this low M. Which one, high M or low M, is going to get there first? How many people think that high mass stars will get to main sequence first? How many people think that low mass stars will get to main sequence first? The high mass actually live their lives faster, and that includes going from protostar to main sequence, and also means dying from main sequence. So high mass stars are going to get there first. So that's kind of the neat thing you see here, the delay. All these stars were born about the same time. You see the high mass kind of filling out main sequence, and then at some point you see kind of a tipping point where these lower mass, they need a little more time to simmer before the protostars actually arrive at the main sequence. So these guys are still coming. Still coming, okay? They're working on it. This is kind of how that works. Beautiful. This is on my list of objects to try to image. You can kind of see this is called a Christmas tree cluster. Gorgeous stars. All right. So here we go. Oops, sorry. No. This one's a little different. So I'm going to put high mass up here because that's how HR diagrams they all work. I'll put low mass down here. So there's no, I'll kind of answer my own question. I won't ask this in the form of the question. The reason that I'm missing the high mass stars is honestly, they have lived their lives. They've left the main sequence. So they might be up here in the giant regions, or we're going to talk about high mass stars. They blow up. They might have blown up. So this is, again, to kind of show you the delay that these high mass stars arrived in the main sequence, lived their lives, and left. These low mass stars, they're still kind of on the main sequence. Okay? Just to kind of show you a different cluster, how these two stars work. All right. Here is another HR diagram of a cluster of stars. The way I would read this one is, of course, this is our main sequence. These would be our, what do we call these? What do you call these guys right here on the HR diagram? I'm not protostars now. They're not protostars. They're like after a star leaves the main sequence, what do we call these? That's the one Reed usually answers, but I'll take it from you. Yes, supergiants. Yep, these are supergiants. So these actually, think of these as actually, these were the high mass stars that left, and these are our supergiants. And this right here is a tipping point called the turn-off point. Turn-off point. Okay, turn off what? Turn off the main sequence. And the lower that turn-off point means the longer that cluster of stars has been around. The higher the turn-off point means it hasn't been around very long. What do you think about this one? This turn-off point. I can compare the two, but they're on different slides. Just based upon if you guys can flip back and forth. The other one was up here, the turn-off point. Now, and I think it's probably on the slide somewhere. If I call the previous one A and this one B with a lower turn-off point, how many people, I'm going to ask in terms of which one's older. How many people think the previous one was older? Okay, how many people think that this one's older? It is older. Because that seems like it'd be a really good test question. Okay, this one's kind of fun because we don't have it drawn in there, but I would have main sequence here. These would be the red giants, and we're not showing the retired white dwarfs down here, but I'm sure there are some. So pretty, so pretty. So this is what you guys told me. You told me that this one would be oldest of all of these, okay, and this one would be older, and this one would be the youngest. If that black line kind of represents where stars are hanging out. Youngest means that they've all just kind of arrived. All right, yeah, and this talks about the turn-off point. Cool. Well, in this class, I'm not going to go into kind of too much the willy-nilly, but can you see where it goes from, let's see if we can do this. It goes from A to B to C to D, and after D it wiggles. Now, all of that, A to B to C to D to wiggling, that's all moving on the HR diagram. And when you see it moving on the HR diagram, if it moves on a plot, you're like, what? It just means it's changing those two characteristics. So I'll do one wiggle. How's that? I'm going to ask in terms of brightness. I'm going to highlight that last wiggle. So I'm going to call this position A. I'm going to call this position B. Which one is the brighter, A or B? How many people think that A is brighter? How many people think that B is brighter? Actually, A is brighter here because this is my increasing brightness scale. So this is brighter. And if I were to actually, and this is dimmer. So kind of near the end of its life, after it leaves the main sequence, it kind of does this sort of up and down in the end. But it kind of gets some swinging back and forth. Okay. What about temperature? What would you say with regard to temperature for A and B? Anybody know? One hotter, one cooler, or are they both the same? They're both the same. Very good. Yep. But they just wiggle with regard to brightness. And it's kind of like it doesn't last very long. This phase does not last very long. What phase lasts the longest?
The main sequence?
The main sequence lasts way longer than anything else. How long is our sun going to be on the main sequence?
Another, what is it?
5 billion?
Another 5 billion, yep. And how long has it been there so far?
5 billion.
Yep. So 5 plus 5,
10.
10 billion-ish. Yeah, that's a long time. Yep. And so this is short, and this is short. Cool. All right. What is the symbol for hydrogen? Yep. H, just the letter H. I know it's weird we call it the symbol. So this guy in here, this purple area, we have H plus H going to form HE. Okay. What is the symbol for carbon?
C.
C. Very good. Kind of here in the oh, I guess this, I'm sorry, I guess that should have been, go up here, hydrogen envelope, H, hydrogen shell fusion. Sorry, final answer. That second one there, it says hydrogen shell fusion. I'm going to put H plus H goes to form HE. Final answer. There here where it says helium fusion, I'm going to put HE plus HE goes to form C for carbon. What's the symbol for oxygen? What letter do we use for oxygen? Oh, yeah, y'all should take chemistry. Yeah, so actually this one, HE plus HE goes to form C. I'm going to put and O. This is actually related to kind of what a low mass, the middle of a low mass star looks like. Low mass, by the way, I'm going to go ahead and put it on the slide. By low mass, we're talking, okay, so it's got to be at least 0.4 solar masses, 0.4 m the sun, and the upper limit is 8 times the mass of our sun. I don't have mine to show you, but on the sheet, on that colored sheet I gave you on Friday, it's kind of got that written in there, kind of those are the kind of boundaries for the mass of a low mass star. Wow. All right. So we've been kind of talking about this. Here, right here, these are our main sequence stars. We see the pretty blue ones up here, the little cute little red dwarfs right here. Okay. And here after our sun, kind of showing you the path of the sun, after it leaves the main sequence stage, it's going to go up here in the giant stage, and you can kind of see it wiggle back and forth in the giant stage. At the end of the giant stage, it's actually going to kind of slough off its gases. Where does it go after the planetary nebula? To the white dwarfs, exactly. Yep. I have some slides kind of showing you different planetary nebulas. And I'll tell you historically, like Mrs. Snipes, planetary nebulas have nothing to do with planets. And you're right. And so historically, the reason they're called planetary nebula is because when people would find them, they kind of have shapes sometimes that they thought they found another planet. Okay, but they didn't behave like planets. They are definitely not orbiting our sun. So these are all planetary nebula. Purdy. And the different colors mean different elements. And the reason they're glowing is because kind of the stuff in the gases have been excited by kind of the central dying star on its way out to becoming a white dwarf. Planetary nebula. So why do we have so many different shapes? Well, it kind of depends on our point of view, and it kind of depends upon the physics of the star that's dying. Okay, so this is showing you what is region, well, I guess I won't really put it that way. A is, of course, the giant stage, supergiant. B is kind of a planetary nebula stage, and cooling down to C, that's just kind of our white dwarf. The caption says this is kind of what a star like our sun, how it would end its life. Okay. So what is it with the white dwarfs? Okay, so white dwarfs are down here. And I think one of the videos that I'm thinking of showing you guys on Friday goes something like this. This is our sun, right? And in order to become a sun, to turn on, it had to have all this gravity create that crazy dense conditions in the core and heat in the core to begin nuclear fusion. So our sun does its thing for 10 billion years. Okay, it goes ahead, it leaves the main sequence into a red giant. Okay, but kind of as it wiggles in the red giant area, it actually goes under even more gravity, more squishing. And I kind of liken it to at Christmas time when you get wrapping paper. You've got like a ton of crap load of wrapping paper that you need to take care of. I mean, you love Christmas, but you have wrapping paper. So you have one trash bag. So you proceed to go ahead and put all of that wrapping paper in that trash bag. Like, I only have one trash bag. So what do? You start to stomp on it, okay? You're like, oh, I can get just a little more. And you got one of those sort of trash bags that are really strong. So you crash it more. Like, I can do this. I only got one trash bag. And so that's kind of like what you're doing is kind of creating the gravity, kind of what happens with a star that has lived its life and is on its way out to a white dwarf. White dwarfs are very, 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 very compact. And actually, they're not even quite as, there are two objects that are even more compact than that. But what the slide says, though, if we were to visit a white dwarf, which our sun is going to become, first off, it would be mostly carbon, kind of a carbon orb. And I kind of like to tease that, of course, diamonds are carbon. So they're like, hey, there might be these white dwarfs that are just pure diamond material. But the other thing is, if you were to land on the surface of the white dwarf, which might be problematic, to pick up 1 teaspoonful, it would weigh 15 tons. I'm just saying, that's how much you have crammed it together. So I think that is so cool. So there was a Professor Chandrasekhar who actually said, that's all well and good. Go ahead and take your one trash bag and do this to it. But at some point, there's a tipping point. You're like, you cannot cram anymore. And it's not because your bag's going to fail. It's because you can't get the atoms of your wrapping paper any closer together. And that is that critical mass is 1.4 times the mass of our sun. So you have to stop. We'll talk about more about why that is a stopping point. But that's the high mass of a white dwarf. So I think we talked about this before. They're bright star Sirius. And if we look in different wavelengths, which is on the right, we can actually see it has a companion star. That companion is a retired white dwarf. And then I kind of leave with, these are actually planetary nebula that a few years ago that I imaged. So it's called the Dumbbell Nebula, kind of those two. I can't remember what this is called. Well, that's a good stopping point. Good job, guys. Or good job, me. And so, yeah, next on Wednesday we're going to be interrupted by folks, high schoolers coming through for sneak a peek. So we'll just kind of see how that goes. Kind of wondering if they might want to hear more from you than me, but we'll see. I don't know. 10 minutes.
Do you want this stuff back to you?
Yeah, I'll take that stuff. I'm like your keeper of the trip. Thank you. So I'm going to give all this back to you. And I can't decide. On Friday, you guys can think about it. Let me know if you guys want this to study from, and then you hand it in after the test. Let me know. Problem is, if I give it to you Friday and you forget it to bring it Monday to test, then I'll buy it. So I don't know. I'm open for suggestions.
I think if they forget it, then sucks for them.
I know, because it'd be nice to study from. So. I just can't have you like adding stuff to it, which I don't think you guys would anyway. So I want it frozen, whatever we do. Cool. So remember, you guys can do your. I have extra homework sheets. I think if anybody wants one. Remember, you guys can hand them in early for 11 out of 10 points. Like, how cool is that? I have 2.